Hey guys, this looks like a fun one. We're given three semicircles arranged like this, and it wants us to find the total shaded area. That's going to be the area of these two semicircles. This is day 22 of the 2025 Advent calendar. And if you want to try this one, pause it right now, because I'm going to solve it in 3, 2, 1. So first, I think I'm going to have to make two assumptions. The first assumption is that the center of the red semicircle is the center of the yellow semicircle. I'm not exactly sure how to prove it, but I think it's safe to assume it. And there's one other assumption I'm going to make. This tangent line, which is the tangent line of this red semicircle and the tangent line of the blue semicircle, I'm assuming this tangent line is parallel to the diameter of the yellow semicircle. Let me know in the comments if you know how to prove either one of these, or if you disagree with either of my assumptions. Now for the first step, from this tangent point, I want to draw this line perpendicular to the tangent line. This has to go through the center of the red semicircle. A radius of a semicircle is always at right angles to the tangent point. And the converse is also true. If you have a tangent line and you take a line perpendicular to it at the tangent point, it'll always go through the center of that circle or semicircle. And then since this is a radius of the little semicircle, let's label it little r. And then we can extend this to the diameter of the blue semicircle, and this will also be the center because this tangent line is also tangent to the blue semicircle. So our right angles will go through this center as well. So this whole thing is going to be a radius of the blue semicircle. Now let's look at this diameter of the blue semicircle. It's going to have a length of 3 plus 1, which is equal to 4. So if the diameter is equal to 4, the radius, which is here to here, will be equal to 2. And this radius is also going to be equal to 2. And then since this is equal to 1, this piece here is also going to be equal to 1, because 1 plus 1 is equal to 2. And then next, let's bring back the diameter of the yellow semicircle. And I assume the center of the red semicircle is also the center of the yellow semicircle. So this is going to cut this diameter in half, making each of these equal to big R. And then since we assume this is parallel to this will also be at right angles. And now we're done with this tangent line. And we also have everything we need to write an equation for the total shaded area. It'll be equal to this semicircle, which is pi little r squared divided by 2, plus the area of this semicircle, which is pi big R squared divided by 2. This looks important. Let's put a box around it. And now we got to try to find the values of little r and big R. Let's extend this all the way to here, and let's label this distance x. And then since this whole thing is a radius of the yellow semicircle, it'll be equal to big R. And if the whole thing is equal to big R and this is equal to x, this last little piece is going to be equal to big R minus x. And then from here, let's focus on this right triangle. And since it's a right triangle, we can do the Pythagorean theorem. It's going to be equal to the quantity big R minus x squared plus big R squared equals 2 squared. And now when we multiply this out, it'll give us big R squared minus 2 big R x plus x squared. And then we can bring down the big R squared, and on the right hand side, 2 squared is equal to 4. On the left hand side, let's rearrange things a little bit, and big R squared plus big R squared is equal to 2 big R squared. And I'm not sure what to do next. Let's put a box around it and bring it down here. Now for the next step, let's complete the yellow semicircle and make it an entire circle. Let's extend this up to here, and let's focus on the yellow circle and these two chords. This is a radius of the yellow circle, so it's going to be equal to big R. And now we can write another equation using the intersecting chords theorem. Anytime you have two chords intersecting in a circle, it'll always be true that A times B is equal to C times D. And that's going to be true for any pair of intersecting chords. So now we can do it for up here. It's going to be big R plus big R minus x times x is equal to 2 times 1. And then we can clean this up. Big R plus big R is equal to 2 big R, and then we can distribute this x to each of these terms. This times this is 2 big R x, and then we're going to subtract x times x, which is equal to x squared. And on the right hand side, 2 times 1 is equal to 2. And now what should we do from here? Okay, we have an x squared right here. I want to get this x squared all alone so we can substitute into this equation. Let's get rid of this up here, scoot this up, and let's get this x squared alone. We can do that by adding x squared to both sides, and we can also subtract 2 from both sides. On the left hand side, these are going to cancel each other out, and we have 2 big R x minus 2. And then on the right hand side, these are going to cancel each other out, and we end up with x squared. So now that we know that x squared is equal to all of this, In the place of this x squared, we can plug in all this. We can set it up like this. So this x squared is going to change into all of this. And then negative 2 big Rx and positive 2 big Rx are going to cancel each other out. Let's smush everything together and add 2 to both sides. On the left-hand side, these are going to cancel each other out. And on the right-hand side, 4 plus 2 is equal to 6. We can divide both sides by 2, and we end up with big R squared is equal to 3. And that's really good news because big R squared is one of the things we needed down here. In the place of this big R squared, let's plug in 3. And we can rearrange it a little and scoot it over. And now we got to solve for little r. We don't even have a little r on here, but we do have a big R. So let's solve for big R. We can square root both sides of this. Since big R is a positive distance, on the left-hand side, this square root and this square are going to cancel each other out. And on the right-hand side, we can leave this as square root of 3. And now we know the value of big R. Let's see if we can solve for x. In the place of this big R, let's plug in root 3, and now we have a quadratic. Let's set it all equal to 0. We can subtract this from both sides, and we can add 2 to both sides. On the left-hand side, all of this is going to cancel out. And on the right-hand side, we're going to have x squared minus 2 root 3x plus 2. I have no idea how to factor this. Let's do the quadratic formula. And here are the notes for the quadratic formula. Anytime you have ax squared plus bx plus c, it'll always be true that x is equal to negative b plus or minus square root of b squared minus 4ac whole thing over 2a. And here this is with all those values plugged in. Negative b plus or minus square root of b squared minus 4ac whole thing over 2a. And now let's simplify this. Inside here, this squared is going to go to each of these. So the negative 2 root 3 squared will change into negative 2 squared root 3 squared. Negative 2 squared is equal to 4, square root of 3 squared is equal to 3, and 4 times 1 times 2 is equal to 8. Let's smush everything together, and 4 times 3 is equal to 12, and 12 minus 8 is equal to 4, and square root of 4 is equal to 2. And then on bottom, 2 times 1 is equal to 2. Let's smush everything together, and then we can split this into 2 separate fractions. For the first term, this 2 on top and this 2 on bottom are going to cancel each other out. So we're left with the square root of 3. And then for the second term, 2 divided by 2 is equal to 1. And now we have our values for x. It's equal to square root of 3 plus or minus 1. Let's look at these separately, the plus 1 version here and the negative 1 version here. How are we going to check these out? Since big R is equal to square root of 3 and we have 2 square root of 3's right here, let's plug in big R for each of these. And now we can compare these to this. This says x is equal to big R plus 1. But if we look right here, this whole thing is equal to big R. X is supposed to be smaller than big R, so there's no way x is equal to big R plus 1. So we can safely x this one out. And then for this one, x is equal to big R minus 1. That seems very reasonable. So we can use this as the value for x. So we can change this back to square root of 3, and x is equal to square root of 3 minus 1. We can update that up here. And then for this big R minus x, that's just going to be this minus this. So it's going to be big R minus x equals root 3 minus the quantity root 3 minus 1. This negative will distribute to each of these, so the positive root 3 minus 1 is going to change into negative root 3 plus 1. The root 3 and the root 3 are going to cancel each other out, so we're left with big R minus x is equal to 1. So in the place of this big R minus x, we can plug in 1. And now we can bring all this stuff back. Let's change this big R into a root 3 and this big R into a root 3. And now how are we going to solve for little r? Oh, I see it. Let's get rid of all this and this. Let's move this 1 over here, and we can recognize this distance as the radius of the blue semicircle, and that's equal to 2. Since the whole distance is equal to 2, and this is equal to 1, that means little r is equal to 1, because 1 plus 1 is equal to 2. And this little r is all we needed to finish the area calculation. Right here, in the place of little r, we can plug in 1. 1 squared is equal to 1, and pi times 1 is equal to pi. So we have pi over 2 plus 3 pi over 2, and that's equal to 4 pi over 2. And then 4 divided by 2 is equal to 2. Let's give it a label of square units, and it's already got a box. Let's give it another box. And let's make it bigger, enhance. And this is the answer to our question. In this given problem with our 2 assumptions, the total shaded area is equal to 2 pi square units. How exciting.